All righty, so we're back to the go. I love how every time there's always people that give me looks like you can die now. We're back to the goat. Why didn't you eat lunch? Again, we don't do veterinary degrees in 3 years. Bio class?
Biochem.
Oh, yeah. Okay, so we're up to Coulomb's law. So remember, Coulomb's law is apparently we don't care about our exams. We all just want to fail the MCAT. That's
We've already played for that. Okay.
yeah, but how many trans fats? Still Cheetos. Okay. Yeah. Fine, biochemistry people. How do you know if a fat molecule is not saturated?
Bonds.
It has double bonds. Okay. So we're up to Coulomb's law. This is our basic electric force. So it's going to be the force between 2 points of charge. It's going to be the force that a particle feels in an electric field. So remember, we talked about come on, iPad, stay with me. This is circle. No. And then, of course, we're going to have force vectors. These two vectors are, which way are they going to go? Towards each other. Give myself a little more room. And so, of course, again, someone remind me of how we read that. So F12 is the force on 1 by charge 2, and F21 is the force on charge 2 by charge 1. And then we said what? Yep, so negative F21. That's not, I mean, that's not, this is not as much of the case as much of the time as it is with mechanics, because of course, in this case, we're dealing with 2-point charges. In the future, you might be dealing with an electric field that's coming from a stationary object. To tell you the truth, even though a particle won't move a large stationary object, it still feels the force. So maybe this is, I need more headache medication. Okay. Let's start, what we're going to be doing here is your first foray into what we call superposition. So we have 3-point charges. Find the magnitude and direction of the electric force on charge 3 due to charges 1 and 2. Now, whenever we're looking at this, something like this, the charge that we're looking at, you treat it as just a point in space. You're only going to have to calculate 2 forces. You're also not going to worry about the force of charge 2 and charge 1 on each other. You're only worried about what charge 1 does to charge 3 and what charge 2 does to charge 3. So let's start saying, well, I can do that. Go ahead and draw this here. And so, of course, you notice we have our right triangle there. Yeah, we can make that. We can't really see that one, can we? That'll work. Okay, so we have our triangle. And now there's going to be two forces that are present on charge 3. We have positive X and positive Y set. Okay, so let's say force 3-1. Which way is it going to point? To the right. Why is that? Well, same sign. They're both positive charges, so they're going to repel. We have that vector. What is the other force vector that we need?
Coulomb breeze.
Yep, so which way is it going to point? Towards 2.
So the 2 is positive.
Yep. So again, with your charges, you're going to have forces between positive and negative pointing towards each other. If it's positive, the forces are going to point away from each other. So now we have two vectors here. So now we have to figure out the total force on charge 3. So let's just start with the force 3-1. Okay, so what we're going to start with is we're going to say so remember, this is calculated magnitude. If we go back up, if you wanted this to be a vector, now at first, you know how we've been using unit vectors to denote direction? When you have a generalized direction of your vector, you can call that like r hat, because remember that, yeah, I see you. The connection between the two charges is that distance r. So of course the force is always going to point along the connection between the two charges, either towards or away. And so if you wanted this to be a vector, you could just generalize it as the r hat direction. But for right now, the Coulomb's law we're using magnitude. So then we have the Coulombic constant. And since this is charge 3-1, we're going to use Q3. Q1 over R31 squared. Okay, so I really wish the internet was working, because I wanted to ask this on a quiz. What does K equal? I don't want them numbered. Does anyone remember that?
Okay.
Well, K is Coulomb's constant. No, see, if this was a quiz, it wouldn't be the number. One of the most famous constants in physics, because you remember epsilon 0 is the permittivity of a vacuum. That's essentially the capacitance of space. See? Okay. So, but we'll go back to numbers. So your K value Newton's meter squared over Coulomb squared. Now, how am I going to put Q3 and Q1 in? Well, yes, so they're going to be their positive values since it's a magnitude. But look at the units on them. What are the units on the charges? Mm-hmm. So they're in microcoulombs right now. So does anyone remember the suffix for the scientific notation for negative what?
6.
6. There you go. So let's see, Q3. And then we're going to have 1.2. Over. What's the distance between Q1 and Q3? 1.2. And when you calculate this, you're going to get about 0.00150 newtons. Now, we have two force vectors here, and we need to find the overall, the total electric force on charge 3. Once we find everything, how are we going to add that together? Go back to the homework you had. I'm going to have to specifically add these as what? Vectors. How do I turn this number into a vector? This one's super straightforward. Yeah, the entire force vector is in the x direction, the positive x direction. So the vector itself, so that it only has the one component. It only exists in a single dimension. Oh, I thought I was going slow.
Yeah, it's just like.
Oh. Oh, yeah. Well, we'll do the best we can. I wonder if that means when Zoom is recording, it's going to be all choppy and lagged. Yeah. We have a hotspot. Okay. Let's look at force 3-2. Let me guess, you once again said something that you're not going to be happy is going to end up on YouTube. Okay. Okay. So, of course, this time, Coulomb's constant again. Q3, Q2, over R32 squared. So the constant like, are you talking about writing out the form of Coulomb's constant each time? Yes, you have to write it out. Yep. Yep. Yep.
No, I always do. Yeah, like I forget to write.
Well, that's why I'm stressing it, because because last semester a lot of people kept forgetting to do the vector component form when you're adding things together. Also, like I said, there was a lot of people trying to add X and Y together. It's like, no, those are different dimensional realities. Okay, so then Q3, of course, is our 0.2. And then Q2 this time is the negative. So, well, you can't see it. It'll get there eventually. Q2 is, remember, it's the negative 0.6 microcoulombs. However, we're using magnitudes. So you're just going to write it in as 0.6 microcoulombs. You see it up there? Including the negative sign, because these are magnitudes. And I just did it. Whoops. And then you can see it. What do we think the R distance between Q2 and Q3 is? Yeah, 0.5. Okay, so you multiply that all up. The magnitude of this vector is 0.00432 newtons. Now, how does this turn into a vector? How do we vector component form this one? It's all in J hat. It's all in positive J hat. So now we're going to do the part that you will come to know as the superposition of the forces. We do it more with electric fields, but it's the same idea. Superposition. And so this time we have F31 plus F32. Now this last semester, this is where some people were having some issues because you wanted to take them, like when we were looking for the total force, you wanted to take the magnitudes and add them together. And here's the problem with that. That will work some of the time, but it won't work all the time. The only way you know you're getting the right answer all the time is to form vectors and add the vectors. So of course we know that this is F31x plus F32x. That's our new I hat. Yeah, that's 3-1. Oops. So remember, when we add vectors, we add the components together. Okay. So for this one, so F31 only has the x component, so that's 0.00150 newtons plus 0 I hat. And then there's no y component for F31, so that's 0. Then you have the so your total force on charge 3 yes. I don't know how many points you would lose, but if you did it enough times, I don't know. With you, it depends on if I'm annoyed that day. Like with some people in here, I take no points. With you, lots of points. So we now have the total force vector. Now here's a question. We're going to draw this in. Which quadrant is this in? First quadrant. All right, so what do we need next? We have the vector. Magnitude. So you'll see the textbook do this. The total force, you can just call it F3 because it's the force on particle 3. It's just the total force on particle 3. I'm looking forward to, I have a problem in the slides where it's the acceleration of a proton. I was really surprised. You're talking like nanocoulombs worth of charge produce an acceleration on the order of 10 to the 13th. Where it's a tiny, tiny charge will move a proton to near the speed of light within seconds. It's amazing. And then if you're making a beam out of that and we put neutrons, oh, come on. Okay, you guys took physics last semester. What happens if I put neutrons on the beam? Why would I do that? Not just protons, but neutrons as well. Uh-huh. And it's going to double the watt of the particle beam. Well, you could have a number of answers there. Momentum, kinetic energy. So yeah, if I just use the deuterium isotope of hydrogen, I could more than double the momentum of the particle beam. So what's our formula for magnitude? And we all know I don't like drawing the square root symbol, so we'll use the 1/2 exponent. So plug our numbers in. Jana, you even have to use newtons on this. Okay, you can do that too.
Even,
No, Jana does. Yes, yeah. Well, that's not good. No, class will continue. You're just gonna have to figure out what to write down by what I'm saying. I mean, I could. Then when you calculate this up, you're gonna get a magnitude. So you could also call this, if I move the decimal point there, what's the prefix on Newton's gonna be?
micronewtons?
I'm not sure of that.
Sorry, I didn't even.
Now, what else do we need for this vector?
Direction.
Direction. Oh, we're running out of room. So remember our direction. The inverse tangent of y over x. This is kind of keeping up.
Is it live?
Nope. Yep. So the direction of the vector is going to come out to be about 70.9 degrees. So we know the total force vectors in the first quadrant. It is a positive angle, which means it goes which way? Counterclockwise. Yes. So it's going to lag for you, but you'll see in a second. So what we do is we're going to go back up. And we're going to say, well, that means that vector is going to come right out of charge 3 up to the first quadrant. At an angle theta of 70.9. It's coming, don't worry. Maybe. Oh, there it is. There we go. So that's the total force on that particle. So if that particle was moving, it'd move off at that angle of 70.9 degrees, even though it has two individual forces on it in only X and only Y. Now, when this gets down there, you're all going to try it yourselves.
What?
Yeah,
Dang it.
talk to your friends. Yeah. Yeah.
You have to-
Remember, your forces are always going to go along the direction next to two charges. So either whether that's away or towards, you look at the line that connects the two charges, your force vector has to go along that direction.
Right. I'm doing.
Piper, we don't hit.
Oh, yeah. I'm gonna do one.
My God, I didn't know your face could get red.
No, this is.
Oh, her face gets red all the time.
What's the tomato on the- What? I didn't know. Why? I love that.
So you drove here with the air conditioner? Oh.
Then. What's the premium?
But you're gonna have to.
Yeah, I can do that part.
Yeah. So those two, the only thing that this over. We don't know this is, hey, ever, the first one down, that's the issue. I never. We don't.
Would you able to pulse it for keeping those thoughts?
But just this.
In the same direction of the line.
So it's 10 squared.
So you see that vector becomes a positive, it's going to that. Oh. Yeah, we should talk about that. Huh? Yeah. Centimeters to meter, like, between centimeters and meters, 2 decimal points. So, yeah. Okay. People in the dorms, how are you doing with internet connection? And I can't print, I can't copy.
Yeah.
I can't because all of our printers, they have some kind of software and they get connected. Oh, did you?
They just put it in, like, I put it
Well,
all in now.
I'll test that, but until we get a solid solution to the issue, there's not, we're gonna have to forego quizzes and exams until we get there. Darn it, you said wrong. I'll put that up tonight. We're gonna be doing electrostatics. Ah, shoot. I can't.
Well, they have to say you see, I was told one of those gonna go till 10, but so it should be fine, we just don't have any problems.
I'll put it on the USB. I'll try. As of now, we're still having a lab. I'll get it printed out as I can. No, there's not, because some people won't be able to access it.
Yeah, I'll hold on.
They go to McDonald's, they got free mic.
The problem is not that I can't put it on my job. Yeah. Yeah.
I actually don't think I'm allowed to tell you the solution.
Well, that's.
Fine, everyone goes and takes quizzes with Toddy down at Ebro.
Some kids will log out here. And we have issues in that, and these kids in their accounts, so some people that can't.
Oh, we're gonna have to. Everything else is gonna have to wait until we do some kind of permanent source fix. We'll figure that out as we go. I'm not gonna have you do a full day of one. Yeah. Yeah. Are you guys, who has an answer to the problem? These two are working on it, those two are working on it, she's working on it, we're doing nothing, you're doing nothing.
It was, I was a bit writing back.
Okay. We'll start taking a look at this.
I never had vectors.
Did you?
The one's easy, but the other one you have to do like that.
Yeah, so we're looking at the total force on the 1 microcoulomb charge, okay? So for me, the first thing I like to do, but yeah, it gives you the positive and negative, but I actually want to be able to see where my forces are going to go. So between the negative 0.6 microcoulomb and the 1 microcoulomb, so that's going to be an attractive force. That one has to go, that force is a repulsive force, has to go that way. Again, what? Because it has to go that way.
No.
Like that. We didn't know what we thought about.
Oh, well, then it doesn't matter. You want any pain? I don't. Oh. Your minds. My crystal ball runs on Wi-Fi. I would have at least thought you would have behaved with your mom present, but no.
I think it's better than.
Yeah, we're at.
Yeah, the two girls with those. I was looking for here. Yeah, that was my number one sisters. What was that group? I wasn't very.
Our hop interviews. Yeah, they were all, I think they were all radiography. So now we also have some things we want to know. So what am I doing here? And what am I going to try to figure out with this?
We have to find the F3 and the Y and the F3 and X's.
Yep, we do. But you remember, I have to have the separation distance between the charges. Between the negative 0.6 and the positive 1, I don't have a distance. Yeah. So I just labeled my sides ABC. We know in the Pythagorean theorem, C is always the hypotenuse.
It's easy. It's 3, 4, 5 triangle.
And now for those of you who are crappy to your high school teachers, when am I ever going to use this?
That's from the 3, 4, 5.
So that distance in the +1 microcoulomb. It's getting there. See, this is why I'm wondering why you two keep sitting further apart. Yeah, yeah. Let's work on it. Am I allowed to pepper spray students? Oh, God. He's like, yeah. Okay, so now we need to know F31 and F32. Okay. Let's do, for you guys, it's F32. For me, it's F31. I'm going to do that one first because it's the easiest one to turn into a vector. Why? Yeah, it's only on the negative, and it's going to be a negative I hat. You see that?
Yes, okay. I'm just starting with.
Now, Q3. Coulombs. And then Q1, well, the negative one. And that's why we needed that distance. This is going to be a magnitude of 1.5 newtons. And then, so of course, okay, well, who's confused by what I just did there?
Wait. It's not time to end the evening.
Shouldn't be, no.
What the heck am I calculating?
Don't ever, ever, ever trust your calculator's order of operations. Why did I call that a negative 1.8?
Because it's going to.
Oh, because when I was writing this problem down, I just used the extended version. I made slides on 2 different days. You can use 8.99, that'd be fine. I think you had the answer. Yeah, it's negative X. It's in the negative X direction, so it has to be a negative I hat vector. Now let's look at the one that's a 2-dimensional vector. Okay. Now to help me, what I did was I redrew this. Oh God, you guys you're on McDonald's now. All right. You know what I still really hate about all of you is you guys actually go to McDonald's. I try to avoid it, and I'm the one who's freaking huge. I eat vegetables. And fruit, and y'all are skinny. Okay.
No wonder why.
Needless to say, I don't like any of you.
You said you don't like it.
Yes. Okay, so remember, well, when I was your age, I could stress eat. Can't do it anymore. Now, remember that's our right triangle that our charges are on. So the vector we're looking at now. Does anyone know why I drew this? Yep, and to find out X and Y, I have to have what? The angle. So this is F32. And we have our X and Y components. What we do not know is theta. Why did I draw the triangle in on the other side? Well, not this time. You're close.
Yeah, it's just that angle right there.
What the angle right where?
Yeah,
Oh,
opposite interior.
you mean that one?
No.
Oh,
Opposite interior angle.
close. That's what Sonia said. Diagonal angles. Diagonal or vertical angles is what it's called in geometry class. Opposite interior angles is when you have two parallel lines bisected by a singular line. The angles inside the parallel lines created by the bisection line will be equal to the opposite ones will be equal to each other.
So now we have to do reverse like tangent.
Uh-huh. Well, I mean, so what? I remember I called these A, C, and B. So the way I did it, I mean, even if I didn't have B, I could just go ahead and do this. Do you know how I got here? Well, I know you know how I got here.
That makes so much from house. Say 45 was a little bit.
Yeah, I heard you guys talk, and I was like, well, that's a bit off. The what? Well, no, we're doing the total electric force on that charge. You can play semantics all you want. Try it on your assignments. Well, so because you knew what I was. You knew. Okay. What is the electric force due to the other two charges? That's what it says. What is the electric? All right, I'll put total force from now on. You're going to do a lot of superposition. Okay, so now we have theta. Now we can start looking at our components. And we are going to try to bring more geometry in as we go along, because by the time we get to optics, it's all analytical geometry. That's a fun thing, though. That's how Isaac Newton invented calculus. He used analytical geometry. He just started taking segments, line segments at smaller and smaller and smaller distances until they were infinitesimally small. And that's how he came up with the notion of the derivative. Oh, let's see. This is, there we go. So the magnitude of this force, 0.719 newtons. Now, if we look at those components, which trig function am I going to use on X? Cosine. So Y has to be sine. Which one is going to be negative? Y. So we're in the fourth quadrant there. So X has to be positive. Y has to be negative. What are you talking about? Well, no, because go back over a second, because this is the force we're working on right here. It has to be a fourth quadrant vector because the two positive charges are repulsive.
I was thinking we really just look that whole triangle down there.
Oh, no. Nope. The charges, the matter have exact locations in space and time. Ah, crap. We're out of time, aren't we? So we'll continue with this on Friday. And if we can, we'll pick up speed, but our internet connection is god awful. Why? The answer is no. Okay.
But I